a graph showing that is it's the second derivative, right? Okay. So it's a graph of the second derivative, not the graph of f, as clearly stated there. So in the questions here, knowing that is the second derivative here, the question is which of the following statements are true, or about f are true. So on the first one it says f is concave up on less than 0, and then on b to c. Okay. So ultimately, in order to be concave up, what would have to be the case with the second derivative? Would have to be positive. So is the second derivative, we can see a picture of it, is it positive on those intervals? Yeah. So that looks like 1 is good, so that means that either A, D, or E should be candidates at this point. And then number 2 says that f has a relative minimum in the open interval B to C. So somewhere between B and C, we want to know, does f have a relative minimum somewhere in that interval? And again, all we know here is that the second derivative at B equals 0. We know that, right? And at C it equals 0. And at some point in between B and C, it's positive, it's concave up. True. And we also know that at the top of that, there's a maximum between B and C, but ultimately it's a maximum for this function. That doesn't really tell us anything about the actual function in terms of its maximums or minimums, does it? And so I guess the question is, could there possibly be? We know it's concave up on that whole interval. So could there be a minimum? There could be. Okay. But the fact that it's concave up doesn't make it so that it has to be a minimum, does it? If I drew a picture like that, that would be concave up. Okay, but we don't know if it necessarily keeps going down or whatever. Still concave up, but ultimately that would be, again, not guaranteed. And then the 3 part, f has points of inflection at 0 and b. Well, if we look at 0, the second derivative goes from positive to negative, and then at b it goes from negative to positive, doesn't it? Okay, so that would be a true. Those 2 would be true also. But then again, like I said with 2, again, it could have a minimum in there, but based on the second derivative, we'd need more information, would we? Here's one reason why why people might choose that. Because remember, the second derivative test tells us that if the derivative is equal to 0 and the second derivative is positive, then we have a relative minimum. True? Because if the derivative were equal to 0, we'd have a horizontal tangent, right? And if in that area it's concave up, it would have no choice but to be a minimum. True? But again, we don't have any guarantee here that the derivative is equal to 0, do we? So again, it could be true, but does it have to be true? No. So therefore, that's why it would be choice E. All right. Ultimately, A-B question. Just, F prime, F double prime relationships. What else? Through 41. On 40, we have a t of x function. And we're going from 0 to infinity, 1/2 k, and then x minus 3 to the k. This is that over k factorial. All right. So the issue here is that this is a Taylor series for a particular function f, and we want to know what is the value of the 10th derivative at 3, okay, which ultimately is the symbols, but ultimately we're looking for the value of the 10th derivative at 3. Okay. All right. So knowing that this is Taylor series, and knowing that the center is ultimately 3 here because we have our x minus 3. So if we were to start with our first term on this, remember if we let k equal 0, we're going to get simply 1. Because ultimately, this 0 power here is going to give us 0. 0 power is going to give us 1. 0 factorial, remember, is 1 also. This is going to be 1. If I did my second term here, my second term is going to be x minus 3 to the 1 over 1 factorial times a half, if you will. True? Alright, and if I did it, kept going, I'm going to get squared over 2 factorial, and I'm going to have a half squared here. Just going to leave it unmultiplied at this point. And then if I kept going, I'd end up with a half to the third, x minus 3 to the 3 over 3 factorial. And ultimately, when I get to my 10th term here, remember, ultimately just to put some notes on here, remember this is our f of 0, well in this case it would be f of 3 because our center's at 3, so this would be our f of prime at 3, f double prime at 3, and so on. So the number in front here, remember, is it's ultimately our coefficient. So if we were to keep this going, continue that pattern, if we got to x minus 3 to the 10th over 10 factorial, we'd still have a half to the 10th out here, wouldn't we? And remember, our general form of this Taylor series is going to be whatever derivative, nth derivative out in front, x minus 0 or 3 or whatever the center is, and to the nth power over n factorial. And so ultimately that part right there, isn't that going to be what represents our 10th derivative at that point? So if I do 1/2 to the 10th power, I get that, which looks like that corresponds to letter C, which I believe is correct. Good. Alright, so again, key element here, just remember it again when we build a Taylor series, looking at our terms. I mean, we have the means to find the terms whether we know Taylor series or not. You know, we can build the terms because we can just put 0 in for k, and then 1, and then 2, and 3, and build a few of the terms. But ultimately, we know that the general form of a Taylor series is going to be that x minus 3 to the n over n factorial, and then times out front the derivative, whatever n is, the nth derivative, first derivative, second derivative, third derivative, and so on. And so again, that number out in front, okay, and again, they kept it separate from the factorial part, which was convenient, right? Okay. We know that definitely has to be part of it, and then that number out in front is going to be the whatever derivative, in this case the 10th. Okay, so if we 0.5 to the 10th, good deal. So again, you know, in a problem like that, it looks like a pretty complicated problem with factorials and summations and all that business, but in the scheme of things, it's really just 0.5 to the 10th. Alright, so again, it's a PC problem, it's a Taylor series. Anything else in that first group? Okay. 39. We have an f of x, 0.1 to x of sine of 1 over t dt, and the interval is 0.1 to 0.4. And the question says, at which of the following values of x does f have a relative maximum value? So for f to have a relative maximum here, it would have to, the derivative would have to be equal to 0, number 1, true? Or the derivative would have to not exist. It needs to be some critical point. Keep in mind though that we're on an open interval here, so therefore the endpoints are not candidates. Okay, so we're just looking for where does the derivative equal 0. And so ultimately this is just a first part of the fundamental theorem problem. We got the derivative of an integral defined function, it's just the integrand evaluated at the upper limit, times the derivative of the upper limit, but in this case the derivative of the upper limit is 1, upper limit just being x. So this is our function, and ultimately we want to know, does this ever equal 0? Now, if you look at the problems here, is this going to be an algebra problem for us? It's a calculator problem, so punch it in and see what you get here. So, we are sine of 1 over x. And my window, I'm going to go 0 to 0.5. That's really all we need to see. We'll go by 0.1s. And if you count here, here's 0.1, 0.2, 0.3, 0.4, 0.5. So this chunk over here, we don't need to worry about that, which is convenient, right? So ultimately, again, we're looking at a picture of the derivative here. We want to know when if we're looking for when the thing has a maximum, then the derivative would have to go from positive to negative, wouldn't it? So wouldn't it be that one right there? Where the derivative goes from positive to negative? So let's try it. Do our zero command on that. We get 0.159, which turns out to be letter B. So again, it's an AB part, fundamental theorem, part 1. And also, it's fundamental theorem to get the derivative, but then it's also our knowledge of maximums and minimums. When are we going to get a maximum minimum? When the derivative is equal to 0 and changes from positive to negative, our function would have a relative maximum. Alright, what else? We'll go up to 45 now. Anything in the second part? 42. Looks like we have a mean value theorem problem. It says on the interval 0 to b, it says c is equal to 4.522. The number guaranteed by the mean value theorem for the function f of x equals sine x. And we want to know what is the approximate value of b. So remember, ultimately the mean value theorem, in a nutshell, tells us that if we have some function on some interval, that somewhere on the interval the derivative is equal to the slope that connects the two endpoints. So ultimately the derivative at c, there's some point c in the interval, where the derivative at that point equals f of b minus f of a all over b minus a. Fair enough? So in picture it looks like that, in symbols it looks like that. Remember, the mean value theorem guarantees that that's true as long as we have a function that's continuous on the closed interval, differentiable on the open interval. Sine x, of course, is continuous and differentiable always, so that qualifies. So we want the derivative at c, so that means that we want the sine's derivative would be cosine at c, and they gave us c was 4.522. So that would be our left side, the derivative at c. And on the right side, f of b, we don't know b, so we don't know f of b either. Also, ultimately, f of a is sine of a. Sine of a, in our case, would be 0. So sine of 0 we know is 0. And on the bottom we'd have b here. So ultimately we'd have cosine of 4.522. F of b would be sine b over b. Alright, questions so far? So the next issue is, well, if that's the case, then how do we solve that equation? Like I said, ultimately we have on the right-hand side of our expression we have the f of b, sine of b in this case, because f is our sine function, over b. And again, we're trying to find b. Well, again, we could try to do some algebra here, but do we need to do algebra? Could we just calculate it? Do the intersection between these two? That's what I do. And it looks like the choices are in the 3s or 4s there, so I'll open up my window a little bit. We'll go 0 to 5, let's say. And I'll open up the y part too, just to see here. May not need to have done that, but there's our cosine of 4.522, and there's our sine of b over b. So I will change my window back down to, let's go -1 to 1 here in the y direction. See what we see. Looks like we do in fact have an intersection point there. Right? And if we do our intersection command, looks like we get 4, which mind that this is certainly checkable too, because if we just did cosine x, which is the derivative, if we did it backwards now that we know the answer to the b part, if we did f of b, which means sine of 4 minus sine of 0 over 4 minus 0, we'd ultimately have sine of 4 equals cosine x. And ultimately, if we solve this sentence, if we do the inverse cosine of sine of 4, if you will, just check. So inverse cosine of the sine of 4 should get that wrong answer. Oh, divided by 4, sorry. Forgot the divided by 4 part. That's still not right. That better be. That would have been the wrong answer in the first place if I wasn't, right? Oh, I know why. This is, let's do this. This is the first quadrant answer I'm getting because it's cosine inverse. This 4.522 is not in the first quadrant. It's actually a third quadrant if I added pi to that. No, that's not right either. No, first quadrant, that's not in first, 1.76 isn't in the first quadrant either. That's actually in the second, isn't it? Let me get that back on there for a minute. Alright, so luckily we just know we did it right in the first place and we don't have to go through all this. Right? So if I subtract, this is second quadrant would be pi minus theta, so I'd have to go minus pi from this. And just negative 1. So there's your first quadrant. If I add pi to that, there's my 4.522. There we go. I had to work out somehow. Just got to make sure we got the right quadrants. All right, so a good problem, good mean value theorem problem, because it's not as easy as just saying, find c. That's obviously the easiest case scenario. Set the derivative equal to the slope between the endpoints and solve for c. Had to think a little bit backwards, but ultimately it's a similar problem because we just have an equation to solve once we write it from the general. Okay. So it'll be AB, mean value theorem. What else? 45, right? 43 says, what is the approximate value of cosine of a half obtained by using a fourth degree polynomial for cosine about x equals 0? Alright, so if we're going to do our Taylor polynomial, remember we're going to start out with f of 0. Cosine of 0 is 1. F prime at 0 is 0. F double prime at 0. Keep in mind this is the original here is cosine. Negative sine, negative cosine. So negative cosine at 0 would be negative 1, so we do minus, and that's x squared over 2. Minus 1, x squared over 2. We know the third derivative is going to be back to sine. And we know that that's equal to 0. And then we get to the fourth derivative. Back to cosine, back to 1. X to the fourth over 2, or 4 factorial. So knowing that, our general formula then is just minus 1 minus x squared over 2 plus x to the fourth over 4, and we could continue that pattern. And we know that the pattern is going to follow negative x to the sixth over 6 factorial. Okay. And then x to the eighth over 8, and so on. Okay. So with that, the question says fourth degree. We don't need to go any further than that because this is the fourth degree, right? And remember, the whole premise of writing a Taylor polynomial is to write a polynomial function that mirrors the cosine function. Okay? So if I put cosine of 1/2, I can get an answer. But if I also put a half into this, I'm going to get a similar answer. It's not going to be exactly the same, but it's going to be pretty good, depending on how far away from the center I go and how many terms I use in the Taylor polynomial. Okay? Bottom line is, if we do our 1 minus 0.5 squared divided by 2 plus 0.5 to the fourth divided by 4 factorial, which is 24. We get that. However, again, if we started looking at our if we looked at the answers first, we would know that they don't want a decimal for this. We We could, of course, take all 5 of those and see which decimal is the right decimal, but in general, if we have our 1, and then if we put a half in here, we're going to get a half squared, which is a quarter. Quarter divided by 2 would be an eighth, so it should be an eighth. So far D and E are the candidates that look like they're the correct ones. And then if we do the next one, we'd put a quarter into the 4th power, and we'd get a 16th. It would be a 16th over 24. 16 times 24 would give us 384. Yep. Could have just looked at the answers, I guess. It's definitely not 64. I knew that. Right? So therefore, be choice E. So a BC problem. Again, it's Taylor polynomial. Right? What else? 44. In 44, we have an integral given. That's 0 to 1,000 of a to the x dx. And then we have a to the 1,000 of 8x dx. And we know that equals 10.4. And we want to know, what does a equal? Alright, so first thing I want to decide here is with the setup that we have here, we're looking at this function a to the x, which we know is just an exponential function. Right? And if we do, if we go from 0 to 1,000, let's say that this is our picture. That would be that area right there, wouldn't it? And then if there's some number a, okay, that is going to be, let's say, somewhere here, like there, put it somewhere. Okay, if that's our a value, the area from a to 1,000 would be just the right half of that little area that I've already shaded. True? Or the checker shaded part, if you will. Okay. All right. So the question is, if I subtract these two areas, okay, then I'm going to get 10.4 ultimately is what the issue is. True? Now, with this, okay, couldn't we actually come up with an answer for that? It's just a number, right? Okay. All right. And then with that, if we were to do our antiderivative here of 8x, remember our antiderivative, the derivative of 8x, is itself times the natural log of the base. So the antiderivative would be itself divided by the natural log of the base. And we're doing that on 1,000 in a. So if we do 8 to the 1,000, gigantic numbers here, maybe we can do it without having to actually calculate those numbers. And we'd have 8 to the a over ln 8 on the side. All right. So ultimately, I'm going to go ahead and do that same thing over here and see what happens. So that's ultimately my integral here for this one, from a to 1,000. If I do the 8 to 1,000 one, if I do the 1,000 part, it's going to be 8 to the 1,000 over ln 8 again, minus 8 to the 0 over ln 8. ln 8, not L8. So just by doing that, what's going to happen with these two? Those are going to be out of there, which is good because I don't even know if the calculator would do 8 to the 1,000s, but I do might be overflow here. Alright, but then with these two, keep in mind what's 8 to the 0? 1. So we'd have negative 1 over ln 8 plus 8 to the a over ln 8 equals 10.4. True? We have a common denominator here, so we can put those together. Bring it up here, up top, and we'll go 8 to the a minus 1 over ln 8 equals 10.4. From there, if we multiply, see what happens. We got 10.4 times ln 8. We get 8 to the a minus 1 equals 21.626. We'll leave that in the calculator. We're going to add 1 to it. Alright, so 8 to the a is equal to that, 22.626. And if we do logarithm of both sides, we end up with a ln 8 over here, ln of that. So if I do natural log of that answer, divided by ln 8. 1.499999, which ultimately corresponds to letter B, 1.5. Ian?
Could you just take the integral from 0 to a of 8 to the x and equal it to 10.4?
Well, ultimately, yeah, if you, the other alternative here, if you did, and we'll see if that might be a quicker way possibly too, because remember, the way, that's why I started out with this drawing, to illustrate the fact that if I took the area from 0 to 1,000 and I subtracted the area from A to 1,000, wouldn't I have that right there? So let's see if the algebra works out easier on that, because it might. Okay. So if I went from 0 to A of a to the x dx equals to 10.4, ultimately it's going to wipe out some of the bigger numbers. We wouldn't have to deal with those in the first place, because we just have 8 to the x over ln 8, which ultimately gives us 8 to the a over ln 8, ln 8 minus 1 over ln 8 equals 10.4. So notice that by doing it that way, we got to this a little bit quicker. Remember, that's the same thing we had right here, isn't it?
Yeah, and then you can just cheat and use the multiple choice answers to guess if you want.
You could do that too. Yeah, if
Sure,
you couldn't remember how to solve that exponential equation, then you could certainly just see which one works. You could also graph the two sides to see when they intersect as well, so you got lots of options for the solving part. But all right, what else? Okay. 45. Okay, let's see what we got here. We got looks like we have some kind of speed equation here in meters per second versus altitude in meters. And it tells us that in the Earth's atmosphere, the speed of sound is a function of the altitude. The figure above consists of 3 line segments, shows the speed of sound as a function of altitude in meters. And it says the graph is not drawn to scale. What is the average speed of sound in the interval 0 to 32,000? Okay. So the average speed, keeping in mind that we have a speed equation here, S of A. Okay, we don't have a formula for it necessarily, but ultimately we have this S of A. And if we want the average speed, that makes it an average value problem. That means that our answer is going to be found by doing this. Okay. Yeah, it's an average value problem because they want the average speed. We have a speed function. If we want the average speed, we find the area under the curve and we divide by 32,000 in this case, because that's B minus A. So knowing that, if we look at the picture that we're given here, we got a triangle in this part here. Ultimately the area, if we drew a line down here, it's going to be a trapezoid for that part. Goes to 341 up here. This is 295 here in terms of the y value. This is 341, 295, and the distance across is 11,500. So the area of that trapezoid is 1/2 times 11,500 times 341 plus 295. And if we calculate for that part, we get 3,657,000 for that part. Then the next part is a rectangle. So its area is going to be 295 is the height, and it goes across to from 11,500 to 22,000. Should be 10,500 times 295. Oops. There we go. And then the last part again is a trapezoid. The height's again 295, and the height on the last one is 302.5. So its area is going to be 1/2 times that distance across. Goes from 22 to 32, so it'll be 10,000 here. And then 295 and 302.5. 9,987,500. Alright, so if we add those all up, we get 9,742,000. And again, that's our area under the curve. We've calculated the area of the three parts here. And if we multiply that by 1 over 32,000, get 304.4375. Looks like the nearest tenth is the letter C. The other alternative here too is could we write an equation for these different line segments and do integrals? With those as our integrand. I would suggest that probably be more difficult though, because it'd take you time to have to write the equation for each of those lines and set up those three integrals. I mean, if they're segments, I'd just use geometry to figure out the areas if I were you. Alright, so that would be AB, the average value. Questions on that one? Alright, any others?